Uh, I'm here to talk about ArrayDeques and in general about Scala 2.13 collections and in particular a data structure called ArrayDeques. While preparing for this talk, I learned how to pronounce this correctly. It's on English.Stack Exchange. It's not ArrayDeque. It's not Array. It's not Array. ArrayDeques, it's ArrayDeques. It's like a deck of cards. All right, so about me. My name is Pathikrit. I work in a hedge fund called Q2 Management. I've been doing for Scala for 6 years. I love data structures and functional programming, so this fits in well. So yeah, let's talk about 2.13 collections. Since we don't have too much time, it's only a 30-minute talk. I wouldn't go too deep into it. Some things, highlights, can build from is gone. If you don't know what it is, great. You don't need to know, you shouldn't know, unless you want to lose your sanity. That's gone. So before, a map looked like this, which is, if you stare at it for a little bit and you know what can build from is, it makes sense, but not really. But now map looks like that, what you thought map should look like. And at a high level, to abstract over collections is moved up here, which is the CC, which is the abstraction. So you can go from one type of collection to something else. All right. So there are some new APIs. I'm not going to give you a tour of the APIs. You can look at the Scala doc. You can click on what's new in 2.13, and you will see the new APIs. Some examples are, this is one of my favorites, where you want to do a group by and you also want to map values at the same time. There's something called group map. So these are kind of like syntactic help about common operations. In place mutable API. So the few of you who do use mutable collections, this is pretty useful. If you have a mutable buffer and you want to filter and map, but you don't want to each time create a new collection. You want to just mutate the mutable collections. You have filter in place, map in place, a couple of these. There's some more. Stream versus lazy list. Streams are gone, lazy lists are in. There's better support for views. Views are a first-class thing, not an afterthought. It's built into every collection. We don't have the traversable versus iterator versus iterable dichotomy. Myself, I don't know on the top of my head which one does what after doing 5 years of Scala. Now it's just iterables. And there's some new collections. So let's talk about ArrayDeques. It's a new collection in Scala 2.13. It's also known as circular buffer in the literature. It's a replacement for most mutable collections. It's faster than a mutable array buffer when you use it as an array, when you're doing random indexing. And it's faster than a linked list when you use it as a linked list, when you want to insert things at the beginning or the end and, or at a particular index. And this is my first contribution to Scala. I have written a couple of libraries before, but I've never actually contributed to Scala Lang, so that's cool. All right, data structures 101. This might be a little hard to see, but this is essentially a table of asymptotic complexity and the mutable collections that you have to offer. So at the top, you have array buffers. So these are basically your array lists from Java, or just vanilla arrays that resizes when you run out of capacity. So the cool thing about array buffers is you get constant time random index. So what that means, you can get the element at an index I or update an element at the index I in O1, which makes sense. Computers have random access memory, and you can go jump into a cell and go update it. You can append to it. You can put an element at the end in constant time, which makes sense. I mean, you already have a pointer, or you know the size of the array. You can just go poop one more at the end. But the moment you try to prepend something, when you want to insert an element at the front of the array, it's no longer constant time. It's a linear time operation, because you have to move everything in front of it to the right. Same for if you want to delete something from the beginning of the array, it's no longer constant time because you have to shift everything left. But if, again, delete last is easy. You just move the last thing back. And this problem happens because why do you have to move things around when you do stuff from the front? Because you still want to have the random indexing property. If you contrast that with something like a linked list, it's kind of the opposite. The linked lists have nice properties where you can append and prepend in constant time because you have a start and end pointer, and you can quickly switch around pointers and insert things in the beginning without shifting everything to the right. You just move the head pointer back. But now you don't have constant time random indexing because if you have a linked list of 1 million items and you want to update the 30,000th item, you have to follow your pointers till you reach the 30,000th item. And this is where ArrayDeques are cool because it's the best of both array buffers and linked lists. You have not only have constant time random indexing, but you also have constant time prepend and append and delete first and delete last. And even the insertions at the Ayat'index is faster than the linked list one, and for the array buffer, it's the how far you are from either end. So if you're inserting at the Ayat'index, it's min of I and the size minus I, and same for delete also. And I'll show you in a bit how we achieve that. There's also Java utils since Java 7 has an ArrayDeque. It has a couple of shortcomings, besides being in Java, which is it doesn't have a public get. It has a private get for some reason. I don't know why. And the insert and deletes are not optimized. The one in the Scala 2.13 is faster. So this one does a very naive one. OK, so let me try to zoom this. There we go. OK, let's start with a very vanilla implementation of an ArrayDeque. So, OK, we create this class, ArrayDeque. Underneath, it's just an array. Initially, let's start with the 64 items in it. All right. And you have a start and end pointer. They both point to 0. And the invariant is the start is inclusive, the end is exclusive. So right now, the array is empty. OK, how do I insert an element at the Ayat'index? So this is the key operation. You do everything offset from start. OK, so start and end, you can assume could be anywhere. It happens to be when you initialize it to be 0, but it may not be. It could both be 17 for all I care. And you do everything with the offset from the start index. And you don't want to overflow the capacity, so you do modular arithmetic. So you do modulo n, where n is the size of the array. OK, and similar for get. So similar to for the read, you do the same thing. OK, so that's simple. OK, how do you append? So append is basically you insert at the end index and you increment the end pointer. And here, obviously, I'm not actually moving pointers around. I'm moving incrementing and decrementing variables. OK. So prepend. Prepend looks very similar to append. And what I did was I decremented the start pointer and inserted the element at the start. So, you can see that you could screw up here and have an off by 1 error, but follow with me here. So the idea is you have start and end pointers, and when you insert at the beginning, you move it back, and when you insert at the end, you move it forward, and you do modular arithmetic all the time to make sure you don't go out of bounds. All right, delete last. This is easy. You just move the end pointer back. There are some caveats regarding garbage collection. I'll go to it in the end because you actually also have to deallocate, but that's details. Delete first. OK, you move the start pointer to the right. And clear. You want to clear the whole array. again, you can just set the start to the end. Now you just emptied out as if you pretend that nothing exists in the array. And lastly, size. This is cute. N minus size, n minus start, and if you do modulo n, it handles the case when start and end are, when start is not less than end. I hope this pseudocode, this code compiles, convinces you that this kind of data structure is possible. If you see, none of the operations are linear time. They're all constant time operations, and I have managed to write an update, an apply, an append, a prepend, a delete fast, a delete last, a clear, and a size in constant time. Obviously, if you actually look at the 2.13 code, this is not what's there. There's a lot of devil in the details, like how do you handle resizing? You have to do smarter resizing, which is doubling up at appropriate times, or shrinking down. If you're doing a lot of deletes, you want to shrink it down also at a lot of times. This code also doesn't show you the insertion at the Ayat'index, which is non-trivial to write because there are many cases to handle. And what else? You will see the implementation. Everything is actually done in the 2.13 collection in the Scala repo in using array.copy, which fans out to memcopy, which is pretty fast. So this doesn't do that. This is just for the slide to show you a minimum viable data structure. And I hope that makes sense why it's now called an ArrayDeque. It stands for array doubly ended queue. It has both start and ends, and you can insert at both ends, and you can do modular arithmetic from the start to get to the Ayat'index fast. All right, time for a little demo. Let's see. Okay, so initially, when you create ArrayDeque.empty, here I'm trying to create an empty data structure of characters. As I said, your start and end pointers, which are just integers, they're not pointers, but I like to call them pointers, are set to 0. The invariance is that your start is inclusive, end is exclusive. In this case, there's nothing in the array is empty. And instead of 64, back in the slide, I created a size of 64. For the purpose of this demo, I created a size 8 array. So it's right here. So it's allocated. This little phi means null, which is slightly different from the 0 here. So initially, it's just full of nulls. When you create an empty array, it has nothing in it. Well, at least for primitives, it has whatever the Java primitives is. I think it's the 0-byte SK code. OK. Oh, it's asking me. All right. So what happens when I do an append? Well, I increment my end pointer, which is add 1 to the end, and fill it up here, where I insert at the end pointer, then I increment. So end was 0, and this is where A goes. Inserting a B, that's the same, where I, again, insert at the end pointer. It was at the 1th index, and increment end. So end becomes 2, and I insert at the 1. OK, append C, append D, append E. OK, now this is cool. I want to do a remove head. In Scala 2.13, there is remove head and remove head option for the mutable collections, and remove head option is obviously safer to handle the case when you have an empty collection. So in this case, when you remove head, I look at the start index. So start is 0. I return that, which happens to be A at this point, and increment the start pointer. So and set that index to null. So if you see here, at the 0th index down here, it will return A and set that to null. So let's do another remove head option, and does the same thing. It increments the start pointer, it returns B, and shrinks the size. And if you see, the size of the array is still start minus end, or it doesn't matter, end minus start minus end is 3 or minus 3. But if you do modulo the size of the array, 8, you get 3. So that's the size of the array. Right, so now the remove head option, you get back C. Remove head option once more, you get back E. Now, this is cool. I'm going to do a prepend. So what does prepend look like? I decrement the start pointer and insert at the element. So in this case, start was 4. I decrement it, becomes 3, and insert F. So I'm doing q.append F. So the way this diagram works, this is where the operation is. This is the internal state of the data structure, and this is the external state of the, this is also the internal state of the data structure, and this is the external state. So as far as the outside user is concerned, the 0th index is F, but internally the 3rd index is F and the 4th index is E, even though externally you're saying it's 0 and 1. Hope that makes sense. Okay, so append G, append G, it goes to the other end, append H. Now this is cool. So because of the modular arithmetic, when I try to append now, it will append here at the 7th index, but that's how big my array is. But it will wrap around. The end pointer will wrap around, and you see it inserted I, but now end is 0 because it is doing modular arithmetic. It's doing 7 plus 1 mod 8, which is 0. And right, so if I append J now, it comes. So as you can see, the external API is 0, 1, 2, 3, 4, 5, F, E, G, H, I, J. That's the current state of the mutable data structure. But internally, your array is all chopped up. It starts at 3, it goes till here, then it wraps back here, and you have the start and end pointers. And you're doing offset from the start or the end and doing modular arithmetic. Okay, so remove last option. Remove more, so again, it wraps back. So when I again remove from the end, the pointers wrap around, wrap back, and yeah. And after I did enough remove last options, all my array is clean. And you see I ended up with start and end pointer at some random, in this case, at the 5th index. But that's fine because the size of the array is 0. And again, if I do another remove head option, it's going to return none because the array is empty. Append K, so let me do some more appends. So boom, boom, boom. So what happens now? So now the array is almost full, and I'm trying to insert one more, and this is going to resize it will go from 8 to 16 elements. And you see during the resize, it actually moves the block from start to the end of the array, which is KLM, and from 0 to the end pointer into a contiguous sequence here. The way it does that, it uses array.copy, which is memcopy down underneath, which is pretty fast. So it is basically three at most 2 to 3 memcopy operations when it does resizing. So again, I'm going to do some more appends, prepends, and by the way, all this code is on GitHub, so I'll put a link to it. And yeah, it's another resize, and you can see again, it resized correctly. It moves things into contiguous blocks. And clear, again, just sets the start and the end pointer to the same. So if I call clear, it's just, and it also needs to obliterate out all the elements in the cell. So this is a current bug in Scala 2.12 array buffer collections. If you call clear on a mutable array buffer, it doesn't actually deallocate the cells, which means they're not visible to the garbage collector. So that's a bug we just fixed because we noticed it in ArrayDeques in 2.13. So watch out for that. And yeah, so there are two kind of clear operations. There's clear and shrink, because sometimes when a mutable collection, you have already, because of internal resizing, you might have grown the array to a huge size. In this case, clear grew to a 32 cell element, and sometimes you want to also shrink the array. So there is a clear and shrink operation also. In this case, it will shrink back to the default size, which is 8 or 16 in 2.13. And that's it for the demo. So, okay. All right. Right. So performance, as I said, all the operations bottom out to mem copies. All the complex operations, insert add, delete add, anything slicing and moving. So it's pretty fast. Clone, slice, insert all, prepend all. We do preemptive allocations, which means when you're doing insert all, it doesn't actually go one by one, resize, one by one, resize, resize. It actually does a single scan, figures out the optimum final size, and again does a mem copy. There's a cute bit hack. You don't have to do modulo if your size of the array is power of 2. You can do ampersand operation. So I%n is the same as I ampersand n minus 1 if n is a power of 2. Here are some benchmarks. As you can see, it's the only operation that is random indexing a little bit slower because you're paying that bitwise operation for doing the modular arithmetic, but everything else is much faster. In cases like if you're prepending few things, it's asymptotically faster instead of just a constant factor gain. And the cool animation that I did is actually just 30 lines of Scala. It's a cool library I came across at this conference last year called reftree. What it does is you get access to private members of the ArrayDeque, and you can create render of the state, which is pretty cool. It made me generate that slides with 30 lines of Scala. All right, takeaways. Please contribute. Contributing to Scala is not scary. If I can do it, anyone can. There are a lot of cool data structures. People kind of try to love algorithms, but there are a lot of cool data structures out there. There are papers and things that you might be able to have a good time implementing. Visualize your data structures. Use the reftree library. It's awesome. And for instructional purposes, if you're teaching data structures to students. Yeah, go check out 2.13. So all these slides and the visualization code is in my GitHub. And lastly, we're hiring. So we're a hedge fund located in San Francisco and New York. We do a lot of quant trading, data science, Scala, Spark. Come talk to me if you're interested. That's it. Thank you. You have questions?